Okay, we're recording.
Okay, go ahead, John.
Okay, so my name is John, and I'm from Wega, and my research interest currently lies in 3D object detection. And today I'll be giving you a presentation on the current state of the art 3D object detection, proposal generation method, and proposal generation and also detection methods for the current. So it's developed, the paper name is 3D Object Proposal Using Stereo Imagery for Accurate Object Detection, Object Classification, and it's by Shen and others in Professor Erneston's lab in UFT. So for this presentation, I'll go briefly over how the framework of the object proposal generation and of the detection work. I'll be going over just reviewing some of the benchmarks, performance benchmarks that they use, and then go over the key summaries of actual results and talk about some of the contribution and the kind of improvement that could be made over the current state of the. So first of all, the question I want to ask is why do we use proposals for general object detection? Having good smart proposal generation helps us reduce the search space to find the objects and localize the objects we need. And the nice the attributes of these proposal generation methods is having a very high recall, which also contributes to higher accuracy for overall detection accuracy. Another interesting fact that is right now the state-of-the-art classification networks currently have very high performance, and we want to leverage the fact that we want to use these very high performing classification networks also to do people detection, object detection as well. So there's a reason why we formulate the object detection, detection networks in a way that we can utilize already trained models and such. In terms of proposal for 3D versus 2D, we want to work in 3D because object detection problem for autonomous driving is inherently a 3D problem, and we want to be able to localize and better estimate the orientations of the vehicle that we see in our scene. So, and the 3D object proposal does better in terms of occlusion and scale variation, just because of the nature of the inherent the problem for just amounts of images. So, so I'll be first talking over how so in the first section, it's basically they develop a measure of how to rate of what is a good proposal for an object. And basically, that's done by a set of potential terms and also just a basic linear combination, and they score as a weight. Now, in the actual paper, they generate these basically potential energy terms, and you can also kind of think them as like features of a proposal, good proposals, and basically these kind of give us a guideline on how when they evaluate the proposal, what is a good what a good proposal would contain. So I'll go briefly for each of the terms. The first we talk about point cloud density, which just the name say how dense is the bounding box that contains the certain area, how dense is it with point cloud. And just in terms of notation, X is the point cloud and Y is our tuple that kind of sort of it has more terms, but it's a tuple that kind of describes the boundary box we have in question. So it contains the coordinates, the orientation, the class as well. Just a notation also on omega is the actual box of grid that
so what is X, what is Y?
X is the point cloud.
Okay, Y is what?
Y is the actual the parameters that define the boundary. Okay. So the omega is basically the function of the box of grid of that's contained inside the boundary. So we see the so it's basically this equation is the number of the elements on the box of grid that is contained within the bounding box, and basically we sum over all the occupied so basically P of V. V is for every voxels in this voxel grid, whether it's occupied or not. So it will output 1 if it's occupied, and 0 if it's not occupied. So that gives you a measure of density in terms of our potential. So, and
What was omega again?
Omega is basically the voxel grid that's contained within.
Is what?
Is the voxel grid.
Voxel grid.
Yeah. So 3D representation of an occupancy grid.
Yeah, it's very hard to understand you in the back, actually.
Oh, should I like move so that I project my voice?
So,
Yeah, so let me just put some dots here.
Yeah.
So Y is a bounding box, 3D bounding box. X is our voxel grid. Okay. P is whether a single voxel in our voxel grid is occupied or free. Okay. What this potential encodes is just summing the number of free voxels in the bounding box, the number of occupied voxels in the bounding box, and dividing it by the total number of voxels, which is the point cloud, which is what they call the point cloud density.
Omega is basically the span of that.
It's the cardinality of the set. Yeah.
Occupied, it's just with like whether there's actual.
Whether there's a point in the voxel or not.
Yeah.
That's it. Go ahead.
So that's the first potential term. Second potential term is it's another term that we want to kind of encourage less of the free space to be contained in the bounding box proposal we generate. So it has a very similar structure of the previous potential, except now we penalize having free space. So f of b is another function where the f of b would be 1 if the actual voxels in the grid will be considered as free space. Now, free space, you can think of it as, if you're familiar with 2D occupancy grids, you can generate free space based on, what is it? Raycasting, yes. No. So we'll also see kind of a visualization on how that actually look like. And basically this term, if you think about it intuitively, it's trying to push back the actual proposal further to the actual edges of the detection themselves, rather than in between the detections. And you'll see that much more clearly when I show you.
Yeah, so it's not. Can you elaborate the difference between previous was basically looking at points in the bounding box.
Yes. So basically,
And obviously, if there was no object, there would be no points.
well, it's more in terms of the density rather than just having points in it. So like an actual point, the bounding box would have, it's more likely to have an object if the points are dense in a certain area rather than just having certain points. And also, this includes the fact that you don't want to have free space, which is another label for a map.
So basically, if this potential is high, that means that we are sampling an object, for example, that might be behind another object. So what this potential, how this potential is calculated is that we have a camera here, right? We have the coffee cup and my water bottle. We project a ray from the camera to the first occupied voxel. Everything here, we set it to free. Everything else, we set it to occupied or unknown, or not even occupied, unknown. We are trying to minimize, when we minimize this potential, we are trying to minimize the amount of it, because we can't have a bounding box in front of the water bottle, right? Because there's free space. So this potential tries to minimize the amount of this free space inside the bounding box. That's the whole reason behind adding this potential.
So we'll see a bit more intuitively on the there's a visualization of these potential terms later on. So another potential term they use is pipe, which is basically they first get an estimate of the actual mean distribution, mean and the variance for a normal distribution of a car, the average class height. That's what this information encodes. So basically, this term penalizes you for having a voxel grid that is higher than the mean height class of a certain object. So let's say a car. If the voxel that or the bounding box that's given for this term is higher than a regular size for a car, this will be penalized quite far. And you can see in the normal distribution term that if it's around the mean of the car, the term will be dragged down to 0. And if it's further away from the mean, then it will be a much higher term. Yeah. And then the last potential is the height contrast. Now, this so basically what it does is first we take the same height prior information, except now we kind of incorporate the idea that around a certain bounding box we generate, there should be points that are low, the height should be lower. Now, if you think about it intuitively, if let's say you have a 3D image of a car, now if you fit the perfect bounding box on that car, all around the vicinity of that area, there should be really not much point unless cars are stacked together, like right next to each other. So it helps in this discriminating multiple objects. And also, this is just taking advantage of the fact that cars are never really together at the same place. Yeah.
How does this actually help with discriminating between multiple cars? If because wouldn't this not really work well when you have two objects that pretty much somewhat almost overlap? That's the point.
No, if they overlap,
3D, right?
if they overlap, if the bounding box fits on one of the cars, there will be the penalized term because around that vicinity there will be higher prior, which would overlap the second car.
Yeah.
Do you understand?
It's just one term.
All right. So when we actually visualize these kind of prior and potential terms, we can see something similar to this. So we have the basic stereo image. Now we have the depth from stereo, which we can get from stereo imagery. Depth feed, this is what we kind of use. You can see visualization of how the free space would look like. So basically the purple space here is basically what we consider a free space, where this is very similar to what we see in a 2D occupancy grid, where the ranges are the distance measured from the point clouds are yellow, and the space in between the camera and the range point is all considered free space. Now, if you actually think about it, that term would probably put the bounding box around where the points are yellow and black, rather than purple. Right? It will penalize bounding boxes that will contain purple points in this case. In terms of the actual height prior term, this is how it would actually look like if you visualize the height prior in terms of its weight. So basically, if you see for the car, you will see that the average height of the car will be like in the center of the car, and then as the box will go up and down, they will have less weights around the.
What is it prior?
That's the height. That's visualizing the height prior weight terms.
I can't really visualize the depth feed. So how does that actually determine the free space, like the region and that? How does that correlate with the
The green is corresponding to free space in the height thing.
Oh, so
Yes.
the
green is the ground plane.
I understand, but I mean,
Which is eventually free space. Yeah.
That's what I'm. Yeah.
It's similar, but it's not really.
I know that it's not the same.
For the purple here, basically, one easiest example to see is this car, and you can see these will be the point clouds coming out of the car. Now, for each point cloud, if you draw a ray from the camera to the point of the point cloud, that space you would label as free space, and if you just project it down to 2D, this is what you get.
So in terms of the view, is this like
Top down. This is top down. Bird eye view.
bird's eye view? Okay.
So, but in that sense, it's accumulated in that
Yeah.
sense, right?
Yeah,
Because,
yeah,
I mean, true free space, it's not just the way it's
Yeah, of course,
Yeah,
of course,
it's
yeah. One more thing that happens in this paper is that they remove the ground plane before they do anything. So that's pretty important, because else the free space will not appear as this, because there are points on the ground plane, right? So they remove the ground plane and then they do the free space estimation.
So what's
Like
happening
with
with
the
the
fresh-
prior?
Yeah.
What's happening with the prior one, the green?
That's for visualization.
That's
Yeah,
the
pure
That
visualization.
is technically the ground.
Yeah.
Okay. For depth feed, they get.
So the red stuff there would be the average.
With the car, yeah. Go.
So now we know. So this gives us a way to measure how good a proposal would be. So now, how do we select the best ones? So first, we compute the point cloud based on the stereo and disparity discretized in voxels. And then we run the ground plane estimation. In this paper, they use a very simple method which employs superpixels and just a very small neural network to categorize these as ground planes. But the ground plane estimation can be interchanged with other methods, so it's not really some big contribution in this paper. Second, what they do is they do the candidate box sampling, in which here is a bit sort of random sampling, except they kind of reduce search space of the random sampling based on the fact that the car should be on the ground plane. So they remove the kind of the z-axis, the height axis, then skip any of the empty boxes, because we know that empty boxes shouldn't really be in an object, right? And then basically, so for all the boxes that are sampled, we do the scoring using the potential energy term, and then we use non-maximum suppression to actually.
But the sampling is done uniformly, and then it's scored, or you have some sampling that kind of can
just random sampling. Okay. And then basically, so the non-maximum suppression is just to extract diverse proposals, where it's just a method. Just if you have redundant bounding box on a same object, it will just give you the one best fit. So, so now, so how do you select the top few best bounding proposals? They just use greedy selection algorithm, where we know greedy algorithm is based on each iteration finding the local maximum in hopes to find the global maximum. So for the best, the proposal at iteration is the argument here. But actually, when I actually check the code, they sort these in a descending order, meaning.
I mean, sorry, I just one thing I just don't understand. Why would you even sample? I mean, like things like free space, you wouldn't sample there at all.
No,
because you were saying that they discard.
So usually,
why would you sample there at all?
When they sample in free space, there will be actually not a lot of points because they also remove the ground plane when they actually do the sample. So that's fine. So yeah. So for where was I? So for each iteration, they find the best proposal from all the box candidates, such that the intersection over union, which is a measure of how close the bounding box fits, is less than a certain threshold to all the best candidates from the previous before. So we can see how it generates the top best selection based on the previous best candidates. So this is how the visualization looks like if we actually plot out the top 100 bounding box proposals. And the third image is just the ground truth, just for comparison on how the distribution of the random the distribution of where the proposal would lie. So, okay. So now we know how the proposal generation is done. Now we want to kind of go through the detection framework. And this paper actually doesn't have really much novel ideas in terms of very critically the top contribution in terms of the detection portion, where detection portion they use some of the ideas previously from using convolutional neural networks. So I'll be going briefly over why that's being used for this section. So the input of our 3D detection framework is right now the top ranked 3D region object proposals. And the input is also the stereo image data, which can be encoded as RGB, and also the point cloud itself can be encoded as HSJ format, which is the disparity height above the ground plane and the angles of the surface normal for each point. The output now, then what we want to get out of these for every proposal is we want the bounding box convention parameter, which skews and translates slightly of, and then which would give us a better fit of each of the proposals, and class score, and also the orientation, because we're interested in this for driving purposes. So a lot of the concepts that I'll be going very fast over is involving deep neural networks and convolutional neural networks, which is covered very extensively in CS231. So I highly suggest it. That's a good introduction to look at. But basically the formulation where they get this architecture is from region convolution neural net variant and it's called fast RCNN. The fast RCNN first, RCNN first developed in order to kind of what is the easiest way to kind of develop a detection algorithm just from a good classification convolutional neural network. So basically what they do is they first use a proposal selection method. And then what would they do is for every proposal, they would use the warped image and run the convolutional neural net for each of the proposals. Now, if you already read it ahead, or if you're familiar with region proposal networks, you can already see that doing this for each of the regions that is proposed will be very time consuming. So in what they did in improvement over the region convolutional neural networks and the fast RCNN, and instead of doing running the warped features over the warped region through the convolutional neural networks, rather they only run the forward pass once for each image, and then they use a special layer which is called the region of interest feature pooling layer, in order to just grab the proportional size of the features in the final layer of the convolution to do the bounding box regression and also the class scores. So that it resulted in speed up, much more significant speed up from the previous version of just region proposal, region convolution neural nets. And then another very interesting idea that also incorporated is having multitask loss for both the class evaluation scores and also the bounding box regression. Yep. So the current 3DOP paper kind of extends this idea by applying it to the autonomous driving data set and the way and applying to the regions, the proposal region they have generated, and using their kind of feature. So instead of so the same faster RCN architecture is there, except the only addition really is that instead of the proposal that comes, we use our own proposal generated from 3DOP features, and then we have another stream of region of interest pooling layer where they also utilize context information, which is the same as the box proposal, except the box proposal size are just enlarged so that you can capture a bit of the area around the actual object of interest you were trying to look at. Now, what you do is before outputting the final layer, you concatenate all these features, and then you have three different multipass loss here. So you have a softmax for, and then you have bounding box regression and orientation regression at the same time. One thing to note that the bounding box regression and orientation regression here is using smooth L1 loss for robustness, and also they claim that for sensitivity, it's also it's really helpful because since these values are unbounded, having L1 loss results in much more. If you were to use L2 norms, you would have to tune your training training rate or learning rate very fast, so that, or very well, so that it doesn't actually explode into gradients. So,
what was the loss again?
so this is smoothed L1 loss.
Huber.
Huber. So that's, they claim to be so this is in the end, even though we kind of talk about 3D, this is at the end of the day, it's still 2D, because what they do is they project the 3D proposal into 2D into the image plan, and then that's how they do the detection of the whole detection framework. But in order to extend that to 3D, they convert the point clouds into HH8 format and doubles the model into another network where you would feed in also the HHA features and concatenate all the 4 different feature vectors into one, and then put it into final output later. And that's the only really extension. It's the same as pretty much what it was on the previous slide. So that's how they claim they were able to do 3D actual detection architecture.
So the bounding box design the image plane, but then orientation is defined how?
Orientation is
previous
the azimuth angle of your car.
Okay. Just one.
So I'll just go very brief review about the performance measure before I talk about how well it did in certain aspects. So proposal recall is what we really generally want to look at when we just evaluate different proposal methods. It's the measure of how much of the object of the that the proposal extract from the ground truth set. So this really counts on how much precision you get later down the road. And precision is the measure of how much actual positive detection that are indeed true. So you can calculate these two based on these equations there. In this context, when we talk about positive tests, we mainly talk about intersection over union because that's the measure of how closely it fits to the actual localization of the boxes within compared to the ground truth boxes. So you can see the measure that on the right side how the intersection over union looks like. Another very popular measure we use is average precision. Is where when we calculate average precision, what we do is we interpolate the precision by taking the max precision of various different recall. So when you're calculating performance, you calculate the precision based on various different recall rates, and then that can generate a precision recall curve. And then by integrating the area under this curve, you can generate the average precision. And it's used heavily on Pascal challenges as a performance measure. Now, the importance of average precision is that if you want to score high on average precision, you have to make sure that along different recall levels, your precision is always consistent because it's an average. And another term we kind of focus on is average localization precision, where usually in 2D and 3D precision, we work with intersection over union. But localization precision, we just work with Euclidean distance of the bounding boxes. Another really important measure for autonomous driving data sets is that Kitty formulated as the average orientation similarity, where instead of using precision recall curve, what we can also do is find the orientation similarity, which is based off of a cosine similarity, which is defined on the second equation there. The one thing to note is the delta term penalizes for multiple detection, but if you already have a detected object, that term becomes zero when the same object detection comes in farther later down the road. So these are the measures that we generally use to compare different performances between the 2D and 3D object detection and proposal objects. All right, so here the following sections, I'll be giving you kind of a summary of all the key findings in this paper, rather than giving a very extensive overview. So the first thing to note, it might be very obvious, but class-specific weights used for generating proposals. So in this slide, we're talking about just proposal recall for 2D. The best case scenarios are the class-specific, and it's just very obvious to see why class-specific weights would work better than generic class. Second of all, it takes about 1,000 proposals for the recall to saturate around 90% rate. Another really interesting boost over performance they made was in terms of the cyclist recall rate. So if you look at the fourth diagram, it's a measure of recall versus the intersection over union overlap threshold. And we can see that it has very significant improvements over other proposal generation methods when compared. And then lastly, we also see quite a significant boost in terms of when we plot the distance versus recall, it's still able to get a lot of detections along further away as well. So another key important factor to kind of convey in this slide is that the 3D OP really only relies on spatial information. We only use point cloud. Other the proposal generation methods in here visualize either combination of just spatial information, appearance, or either combination of both. But this technique just uses spatial context, and there's a very hidden implication that maybe spatial context is all we really need, or is the major contribution to generating good proposals in 3D space for 3D.
What is the camera resolution? I mean, particularly the last one is interesting. It goes up to 80 meters, but I mean that will be very much impacted by, I guess, the resolution, right?
The resolution, don't remember, haven't remembered the top of my head, but since we're working with disparity, like,
It's kitty data. The kitty data.
Yeah.
So 1324 by
375.
375, yeah, something like that. Yeah.
I mean, it's not the highest
Yeah,
resolution.
yeah, it's not the highest resolution.
But also, that would also impact the runtime of these switches. So that's so this is proposal recall in 2D. So where we get 3D proposal and then we project them into image space. Now for 3D recall, which is slightly a different measure because we use 0.25 for intersection over union rather than 50%. And on the this is plotted over the moderate data. The main thing to take notice is that we still it takes quite a bit more number of proposals to achieve the same recall rate for 2D proposal recall. And also we can also notice that in terms of for cyclists, there's still a lot of room for improvements over increasing the proposal recall for cyclists because that basically caps on how much cyclists we can capture on the road. So that's the implication on the data that's been generated. And the overall proposal generation runtime for all these is about 2 seconds for 2,000 proposals. So, so this is these are another sets of key findings that are kind of very important that I want to mention from this paper. Is that they also study on using hybrid approach, which means they use stereo point cloud for region road classification, but they use LiDAR data for actual plane fit because the difference between the LiDAR point cloud and stereo point cloud is that LiDAR is much more sparse, but they're more accurate for further distance. So you can actually fit a much more accurate plane. So proposal recall using hybrid is they get very significant boost in terms of small object and far away object. So we can see on the right that for cyclists, there's about at least 20% better recall using hybrid data just than stereo, which is a big implication that maybe there's something about accuracy that we need to kind of focus rather than just sparsity. So, and then another clue we get is the highest 3D recall we get is from the hybrid, but 2D recall is still generally okay with just stereo. In terms of detection and localization, stereo works best on 2D detection and easy set for 3D detection. But using the hybrid approach is the best combination for 3D tasks on moderate and hard. And we want to focus on moderate and hard cases because that's where most of the improvement of the current generation of algorithm will need to be because on the easy set it's already saturated with techniques that already cap around 90%. So what we want to kind of focus on the medium and the hard set. So the hybrid combination gives you the highest average precision and also the localization precision. Just a few more points that I want to cover. Also, in terms of network design, joint bounding blocks in oriented regression using one-pass loss result in boosts in terms of overall orientation similarity, but not much for average precision. So if you take a look at this table, I'm not sure if you see the number, but from this number to the rest, you see about 50% increase in terms of orientation estimation. So that gives also another clue that joint estimation, bounding box regression and orientation estimation, it supports each other. And then in terms of contextual branch, where they add another stream of inputs, which is just bigger than the actual detection size, technically has the highest 2D average precision and orientation similarity for car class, only by a small margin, but at the cost of very large, like slightly larger model. And they also in the paper kind of claims that for pedestrian cyclists it didn't work out very well because the amount of data that's required to train with the contextual branch is just not there because the amount of pedestrians and cyclists in the driving data set is sparse compared to cars. So maybe that's a future study for maybe having a very order of magnitude data set would be much more helpful. In terms of using encoding spatial information to HHA's format, it requires much more GPU memory. So they have to cut down on the size of the weights for the convolutional neural net. Instead of having a 12-layer convex, they have to cut down to 7-layer convex. The improvements on the 2D detection is marginal, just a very small margin. But in terms of 3D detection, it claims to have 5 to 10%, which is a significant boost in terms of performance, in terms of detection in 3D. So we keep getting the clue that spatial context is very important for 3D object detection, which is, if you think about it, it would be common sense if you think about it. It's just you're seeing the data back this up. Also, another really interesting note is that 3D detection was scored the highest at 7-layer RGB with HHA with hybrid data, which performed better than the 16-layer RGB input. What that implies is that having a hierarchical appearance feature doesn't really matter, and having spatial context feature to help detection is much more significant in terms of performance. And then lastly they did some studies on the actual how the ground plane estimation kind of affects. So didn't really using ground truth plane didn't improve much for stereo, but if one is considering doing object detection using just pure LiDAR, they claim to suggest to have a very good ground plane estimation technique for the LiDAR itself, or for the use of generating proposal as well. So, yeah, that was just a big one. So lastly, the last few sections I'll just cover some of what is the major contribution from this paper, and also some of the improvement stuff that we can improve on this paper. Is that the spatial? So we keep seeing this clue that spatial information is far more important than appearance for generating good proposals and improving detection performance and localization in 3D. Like I mentioned before, deep hierarchical appearance feature is less important than spatial features for 3D detection. And that the HHA format also increases overall 3D detection. In terms of proposal generation for hard objects, there's also implication that accuracy of the actual location of the point cloud is much important than the sparsity of the actual data. So that's another lesson we want to kind of, it's a hint in which if we want to improve detections in terms of hard data sets, and also very small objects, this is also another kind of piece of a hint we need to take a look at to improve our detection capabilities. And lastly, so I'll just talk about some of the stuff we can improve over this algorithm and some of the shortcomings of the actual this paper. Is that handcrafted features, these are basically engineered features, right? We take these features from intuition. But can we get a neural network to learn these features, such as what faster RCN did for region proposal networks? That's an idea we can still play around that nobody has tried before. The kind of shortcomings of this algorithm is that it relies a lot on prior data. So knowing the average distribution of normal height for a car would be, where that would be a problem. If you run this same algorithm in another section of maybe that has very different distribution of cars, like let's say in Asia, then you will have a very different mean estimates of these data. So that's one shortcoming of it. It relies a lot on pre-processed data as well. So ground plane estimation and stereo disparity as well. It needs to be readily required for this generation proposal to work. And the paper doesn't really claim to have performance. So when they talk about how long it takes for them to generate a proposal, they don't explicitly mention whether this processing time is considered in that time. So potentially that makes it longer to generate these push detection. And even right now, just for the proposal, it takes roughly 1 Hz and 0.5 Hz for the forward pass. So we're nowhere close to actually run these algorithms on a car. So yeah.
What's the hardware? What's the hardware specification?
They use a Python X to train and also for pass. And yeah, so speeding up these algorithms is another approach where we can take to make contributions. And another questionable thing is the increase in model size, which basically doubles in where you have the contextual information for that marginal performance increase. Is it really very questionable? And then one thing I kind of sort of noticed while reading the paper is that Kitty has no 3D detection actual test benchmark. So all they do is test on the validation set. So if they want to compare other 3D detection, it's sort of hard because they don't have a unified test set. So that could be a very good contribution to something that we could create for our own data set. Then finally, there's a lot of still room for improvements in terms of 3D detection for very hard category. So small objects and faraway objects.
Sorry, so you said Kitty has no 3D detection test. So yeah, what's the ground truth that they use with the paper?
No. They have 3D detection data, but they don't test it on their web server.
Yeah, they don't have a.
Oh.
So they just evaluate 2D detections rather than 3D.
Yeah.
Would a 3D detection just be something they can simply add? Because I assume that the test data set would also include the 3D bounding box.
Yeah.
So it's just.
I mean, they could do it.
Add
It's just they haven't done it yet. And
yeah, so we can always annoy them if we want to try it out. Right?
yeah, nobody just tried out. And I think at that time when the Kitty first came out, just they weren't capable enough of doing 3D detection at that time as well. So
How large was the network? How large was the network?
they didn't
How many
specify the
layers?
data
How
range.
many weights? It was like
The network without the HHA, the first network, did not fit on Titan XP when I tried to train it. It might be an error on my side, QDNN's thing, but it's pretty huge. On the forward class, it takes about 11 gigabytes of GPU memory. Yeah.
no wonder it's slow.
So that's basically it for my presentation.
I think Mike has a.
So one thing I guess I missed this. So they use stereo. What stereo? Is that just the ground truth stereo from the data set?
No.
or
It's
what
called
are
SPS stereo. It's a patch-based stereo algorithm that takes about 2.5 seconds per
Sorry,
image.
you said the SPS?
Yeah, it's called
Oh,
SPS
yeah.
stereo. Yeah.
Okay. Oh. Yeah, okay.
It's quite decent. Like
yeah,
in the
that's
closer range, it's quite decent. In the far away range, it's not.
I was wondering because that's quite like if they're assuming that that's.
No.
Like,
that-
like you
no,
mentioned, right?
no,
That
yeah.
like Joe mentioned, that would add a significant.
Yeah.
Like.
It's not ground truth stereo.
Yeah.
It's
No,
natural.
even SPS is. pretty
Oh,
good.
if you want to use
That's good, right?
semi-global matching, it won't work.
No, SPS, if you're
Yeah.
using that, then you're not gonna be able to get a 0.83. Like,
Yeah.
You're not gonna be anywhere near, that's what I was asking.
Yeah.
How much of a computational burden is to pre-process the data?
You can't really, well, they don't mention really specify in the paper, but I think that's just a tactic.
So it's sort of what the point.
You have just to generate the stereo data and some other stuff.
So for 2D object proposals, they mention using RGB. A lot of classical methods you like convert that to HSV or HEV. Have they done any tests with that? Or?
It doesn't matter. It's just
This is a different map.
yeah. It's just a
It
different
is,
map.
it's easier to like for the reason they convert that is because it's easier to pick up like lane markings and stuff, regardless of
I don't think.
shading.
I don't think in terms of such large networks it matters at all which representation you use. Just because the weights can learn whatever variability in the features that you provide. Anyways, so yeah.
I mean, I guess the point was that it's classical computer vision.
Yeah. It's a
Yeah.
hyperparameter. You can test it. If it works better, you keep it.
Yeah,
That's
I was
what
just
they
curious
do.
if
Yeah.
They actually did that test.
Yeah.
Or...
And no, I don't. I don't think. What do you want?
I have a question.
Yeah.
So when you say that using the LiDAR data, did it improve the intersection union
Oh,
the IO?
yeah. Of what?
Did using LiDAR, did it improve the intersection?
Yeah, so in 3D detection and also proposal recall, it has improvement for both localization and also detection.
So the major thing is I disagree with one point here. It's not the appearance features are not of lower importance than 3D features or spatial context features. Appearance features are augmented by 3D context features. That's the thing. So if we just use pure 3D data without color and texture, we will not be able to get this performance. That's the thing. However, there's a limit of how useful appearance features might be. And that's what this paper shows us. So 16 convolutional layers using only color images is not as beneficial as 7 layers of convolutional features on RGB images and 7 layers on an HHA format, which is basically the point cloud. So that's the major thing we need to focus on.
So does the color imagery help a lot when it comes to determining the exact orientations? Like, for example, a card, because I assume it doesn't help at all.
It helps a bit, but
So like, if we have a car, we can't say, like, let's say we're looking at a chunk of the car is something like at the back. We won't be able to say, hey, the car is going in this direction.
you will be able, yeah, you
Yeah,
will,
you can do
but you can't do that for faraway cars, for example, with low resolution.
Oh, okay.
Yeah, that's the thing. But for close cars, yeah, appearance features help orientation, just because the network will learn what the back of the car looks like,
Okay.
and that means that the car is oriented forward, right?
What if the car is towed?
Oh, that's not solvable yet.
It is solvable if you take into account the time.
Yeah.
Yeah.
Okay, Matt, you want to? Okay, thanks, John. John,
I went over a lot of time.
yeah. Can we save it as a PDF or?
Yeah. Well, yeah.
Yeah, we need to put it on the website. Yeah, let's do it.
For classification.